Oh, can you hear me?
Hello.
Okay, I'm gonna share. Okay, and today, after the fix that we have learned in the paper 4, right? The fixed paper, the chapter that we have learned, the magnetic and the electric and the capacitance, right?
Yeah.
Okay, after having learned the three chapter, we are going to learn a new chapter. Okay, and you have heard the new chapter is really about the nucleus and the particle physics. Okay, okay, first let's look at the content syllabus. Okay, and in the chapter we are going to learn how to divide the atom. Okay, and generally we think the atom is the basic unit, right? And in the chapter we are going to redivision the atom, and maybe the atom can be divided into the three part and use the neutron, proton, and the electron, right?
Yeah.
Okay, and I want to know what is the basic unit of the composition of the electron or the proton or the neutron? Okay, so the A.1 is really about the nuclear and proton number and about the nucleus model of atom. Okay, look at it. The first, like the chemistry, okay, and we also use the left top corner, the nuclear number, right? And they represent the proton number. Okay, understand that? Okay, it's seminary. Okay, and look at the isotype. Okay, so what is the definition of isotype? Mm-hmm. Compare with the atom.
The same number of proton but
Same,
different
same,
number of neutron.
same number what?
Proton.
What's the number? Yeah, proton number same, right? Okay, but neutron number differs. Okay, the
Yeah.
problem.
Yeah.
Okay, and because we have the different number, different neutron number, so maybe the atom, if we have a more neutron number, so the isotype they will become unstable, right? And they will become and take the reaction that is the fusion, right? Understand that?
Oh yeah.
Mm-hmm. If the atom has more, okay, has the more neutron because the neutron number has the greater mass, right? Okay, if the atom has the isotype has the more neutron number, okay, so that will cause the atom become unstable, okay, and if the atom become unstable and they will take the reaction and the reaction is the fusion, the fusion that will become from a one number become the multiple number, okay, and this process we call the fusion. Okay, understand that?
Okay.
Okay, and look at that. Okay, first look at work example. And the atom, okay, is the neutral atom. And how many proton? Choose which one. Look at that. The neutron number, the proton number. Okay, choose which road. Which option is right? Mm-hmm.
The last option D.
Okay, because we have now the bottom, right? The bottom part, the 77 represent the proton number, okay? And the total nuclear number is the 180 and 92, okay? And we use the 192 minus the 77, okay? So we got the neutron number, okay? No problem.
Yeah.
And the electron number, same if this one is not ions, it's the neutral atom, okay? So the proton number equals the electron number. Okay, so the electron number is the 77. Okay, so we choose the answer D. Okay, no problem. And look at that. And after we have nerd, not the atom. Okay, and we know the atom has the three part. The first part is the neutron. The second part is the electron. Okay, and the proton. And we want to redivision and divide divide the atom, the proton. Okay, like the proton. If I want to know what is the basic composition of the proton, okay, understand that?
Yeah, okay.
Okay, and in this part, we are going to outline the basic structure of an atom. From the structure of the atom, we know that. And quarks, here is the word. The word is the quark. Okay, the quark. And the quark have the different name in a different generation. Okay, and the quark in this chapter, we regard the quark is the basic unit of the composition of the protein and the neutron. Okay, no problem. And
Okay.
here's another word is lepton. Lepton is the fundamental unit of the electron. Okay, the
Okay.
composition of the electron. Okay, and you can see there are three rows. Okay, and the row one is a generation one. Okay, the row two is a generation two, and this one is a generation three. Okay, and we can see from the structure of atom, we know the quark has the different names across the different generation. Okay, if the quark in the generation one, okay, and the quark has two types. The first type is the up quark. Okay, if the up quark represent the charge is the 2 over 3 electron, right? The charge quantity, okay? No problem. And the
Yeah.
down quark represent the negative 1 over 3. Okay, represent the 1 over 3, the quark, the electron number, okay? And if in the generation 2, we have the different name related about the up quark and the down quark. Okay, and we the generation 2, the up quark is the charm quark. Okay, equal charm quark. Okay,
Okay.
the charm quark represents the same number of with the up quark. Okay, the positive 2 over 3, the charge quantity. Okay, and the strong quark represents the same charge is the negative 1 over 3. Okay, the problem. And in the generation 3, the top quark represents the positive 2 over 3 electrons, and the bottom quark represents the negative 1 over 3 electron quark. Okay, no problem.
Okay.
Okay, summarize. For example, in the generation one, we classify the quarks into the up quark and down quark. In the generation two, we have the charm quark and the strange quark. Okay, and in the generation three, there are the top quark and the bottom quark. Okay, and if they are the up quark, charm quark, or top quark, the represent the charge quantity is the positive, and the charge quantity is 2 over 3. Okay, if they are the down, strange, and bottom quark, okay, the represent the negative quark, okay, the negative charge, and the charge quantity is the negative 1 over 3. Okay, no
Okay.
problem.
Yeah.
So, and every generation of the lepton, okay, this one's lepton. Lepton is the basic unit of the electron, okay, basic unit composition of the electron, okay, and each generation, like the generation one, each generation of leptons has the corresponding the microparticle. The particle is the neutrino. Okay, neutrino. And what is the definition of neutrino? Neutrino is just somewhat like a neutron. Okay, this is because the neutrino has no electric charge and its mass is also negligible. Okay, no problem.
Okay.
Okay, and so summarize the lepton is the basic unit of the electron. Okay, the basic unit like the electron. Okay, the negative one charge. Okay, and if the reaction produce one lepton, okay, and also producing corresponding neutrino, if the reaction process produce produce and the product has the electron, okay, and the we also has the electron neutrino, okay, corresponding the neutrino, okay, the electron corresponding the electron neutrino, okay, and the neutrino has no electric charge, has no mass, and then mass inclination negligible. No problem.
Yeah, no problem.
Okay. And in the generation two, okay, in generation two, uh, the muon, this one's a muon. So muon has the similar to the electron, okay, and electron the charge quantity is -1, and the muon is also -1, okay, and so you can regard the electron and the neutron as the one, just the same type of the particle, okay. It's also the basic unit, okay, basic unit. And if the reaction produce the product has the one muon, okay, and also will produce the muon in neutrino, no problem. Okay.
Okay.
And in the generation three, if we have the another word is the tia. The tia also has the similar with the electron and the muon, okay, because they are hold the -1 electron, the charge quantity, okay? If the reaction also produced one Tia, the -1 charge quantity, and also they will produce corresponding Tia neutrino, no problem. Okay.
How is the neutrino produced?
Okay, because we use the conservation of the mass, okay, and we measure the action before and action after, okay, and we found that there's the one particle, unknown particle, okay, and the unknown particle, and we got the action before the mass is a little bit greater than the action after, okay,
Okay.
understand that?
Yeah.
Okay, so in the generally we think there's no any particle in the product, but we also but in the mass difference, okay, use the conservation of the mass, okay, and we regard the unknown particle because the unknown particle has no mass, has no charge, okay, and we name the charge, we name the particle as the neutrino. No problem.
Okay. Okay, yeah.
Understand that? Okay. And look at it. Okay. And after we have learned the quark charge quark quantity, okay, and the in different generation that we have the different quarks, okay, and different leptons, okay, and so we will take the map. Here's the word is a hadron. Okay, hadron are made up of the quarks and interact with the strong nuclear force. Okay, so if if there is the force between the hadron quarks, okay, like the baryon or meson, okay, and the hadron can be divided into two parts. First part is the baryon. The second part is the meson. Okay, and the baryon has the two example. First example is a proton. The second example is a neutron. Okay, and as for the masons, the mason, okay, the mason is like the one particle is the pion. Another one is the kill. Okay,
Okay.
okay, and so if there's the force happens between the hadron, baryon, or the meson. Okay, and we will call the force is the strong nuclear force. Okay, understand? No problem.
What is the force?
Strong nuclear force. Strong nuclear force.
Oh, okay.
Okay. And if there's the two charge, right? It's the like the lepton, like the negative, the electron, and this one electron, okay? Because there's the two negative charge, okay? And there's the force, right? The rebelling force, okay? No problem. There's a rebelling force, okay? The rebelling force we call the weak nuclear force. Understand? The weak nuclear force. Okay. If there's the positive charge, like the proton, and there's another proton, okay, the two proton, okay, and we can see there is the rebelling force, okay, but the object is the proton to the proton, okay, not the electron to the electron, okay, and because the proton has the greater mass than the electron, right? Okay,
Yeah.
and we call the force is the strong nuclear force, right? Understand now? No
Uh,
problem.
is it repelling?
Yeah, rebellion force.
Oh, okay.
Okay,
Okay, got
so
it.
we call the force a new name. The new name is a strong nuclear force. Okay, if the force happens between the proton to the proton, okay, and we call the force, okay, a call the force is strong nuclear force. If the force happens in the electron to the electron, okay, because electron has the mass is very low, right? Okay, the negligible mass, okay, and the force happens between the electron to the electron, and we call the force is the weak nuclear force, right?
Okay.
Understand? Okay, okay. And the very common biomes, the biome, okay. The biome is one part of the hadron, okay. So hadron can be divided into the two part. The first part of the biome, okay. There's the two examples of the biome, okay. The first is the proton and the neutron, okay. So if I ask a question, the proton is the biome or methane, okay, and we divide the proton into the biome region, right? Understand
Okay.
now?
Yeah.
Okay. And if I ask a question, what is the pion? So pion is another another region, the region in the Mason region. Okay, understand that?
Okay. Yeah.
Understand now?
Yeah,
The
understand.
pion. Okay, and the biome and the Mason are the compilation of the hadron. Okay, no problem now.
Okay.
Okay, and as for the biome, okay, we have to understand this one. Bion is consist of the three quark. Okay, so the proton, the positive charge quantity is the -1, right? Okay, and we will use the quark, the three quark. They will use the three quark to compose the net positive one charge quantity. Okay, and we know the neutron charge quantity is zero, okay? And we will use the three quarks to compose the neutron's charge quantity. Understand now?
Okay, yeah.
Okay. And how about the meson? The meson consists of a quark and antiquark. What is the quark and antiquark? Okay, if we have the positive, if the Q is the positive, 2/3, and this one is the bar, right? The bar, the Q is bar. Okay, and the Q bar represent the anti-charge quantity. The anti represents they will have the inverse, the opposite, the -2/3. Understand now?
Okay, okay. Yeah, understand.
Okay. So we call this one is the meson. Okay, so meson consists of the quark and another anti-quark. So there's the only two quarks to compose the meson, okay? And there are three quarks to compose the biomes, okay? Understand now?
Yeah, okay.
Okay. And we have now the quark has the three generation. At each generation, we have the positive and negative, okay? And the positive, like the generation one, is the up quark, and the negative is the down quark. Okay, look at it. Okay. Here's the antimatter. Okay, what is the antimatter? The antimatter has the same property with the matter. Okay, but there's a one thing that is the opposite, is the charge quantity. Okay, if we want to know what is the antimatter about the proton, okay, we know proton has the positive. Okay, has the positive. Okay, abbreviation the P. Okay, the proton, the proton, the proton has the positive charge quantity. Okay, so if we want to find the anti-proton, the way we write in this one, the -1. Okay, -1 charge. That is the P at this bar. Okay,
Okay.
in the head of the P. Understand that?
Yeah, okay.
Okay, so this one we call the antimatter. Okay, so antimatter has the same other property instead of the charge quantity. Okay, no problem now. This
Okay.
one. Okay. Anti-proton. So we write in this way. Okay. The anti-neutron write in this way. P bar, N bar, right? The head is the bar. Okay, understand?
Okay.
No problem now.
Yeah, no problem.
Okay, look at this one. Okay, look at the work example. The bion, this one, the bion. Okay, this one represents we have the positive, we have the positive two. Okay, the positive two charge quantity was discovered in the particle accelerator. Okay, and we use the accelerated positive pions on the hydrogen target. And the question is, which of the following is the quark combination of the particle? Okay, so the way to calculate which option is the right, and this represent which option has the same charge quantity as the positive two. Understand now? So
Yeah,
choose which one.
I think A.
Why is A, not D?
D is anti, so -2.
Yes, no problem. 92. Okay, and A is the 3 times the 2 over 3, right? And the
Yeah.
charge is 2. Okay, understand now. No problem. Okay, and look at this one. Okay, this one is the lepton and photon. Okay, so this one. Okay, lepton are group of the fundamental elementary the particle. Okay, and we regard the lepton is the basic unit of like the electron. Okay, and there's no any quark in the lepton. Okay, understand that? So quark is not the basic combination of the lepton. Okay, quark is only the basic unit composition of the hadron. Understand now?
Okay.
Okay, and the leptons there are the force. The force is weak. It's weak force, right? Understand now?
Okay.
Okay. So if there is the force that happens in between the leptons, okay, the force that we call the weak force. Understand? Okay.
Yeah.
So unlike the hadron, okay, like unlike the bion and methane, the leptons do not interact via the strong nuclear force. Okay, the weak nuclear force. Okay, and there are some common leptons. Okay, the first leptons is the electron. Okay, and if we produce the electron and in the reaction equation, it also has another product. Another product is the electron neutrino. Understand that?
Okay.
Mhm. Okay, and if we the reproduct has the muon, okay, and also we have another one. Another one is the muon neutrino. Understand now?
Okay. Understand.
Okay. Look at this one. Okay. This work example, okay? The work example just want us to circle okay? The anti-lepton in the following decay equation, okay? So in the decay equation, so we have to circle the matter. The matter is the antimatter, okay? And the antimatter what? The anti-lepton. So choose circle which one? Is the pion or the positive muon or the neutrino muon? Mm-hmm.
Uh,
Circle which one? Which one is the anti-lepton?
positive
First,
muon.
yeah, because the muon is like the electron, right? So we
Yeah.
all normally use this one, the negative. But here's the positive, right? So it must be the antimatter, okay? The antimatter of the lepton, okay? Understand now?
Okay.
Okay. And there's just some difference, some little difference between the muon and the electron. The muon is similar to the electron, but a little bit slightly heavier. Okay, the electrons and the muons both have the charge is the -1. Okay, and the mass is the 0 and 0.0005 U, right? Understand now? So
Okay.
we can use the 1 over 2000, 1 over 2000 of a proton, right? Understand now?
Yeah.
Okay. And the neutrinos are most abundant leptons in the universe and has no charge and no negligible mass. Okay, almost zero. Okay. And we though the quarks are fundamental particles too, and not classified as lepton. Okay, understand now?
Where does the neutrinos exist?
Mm-hmm.
Where do the neutrinos exist?
Why does the neutrino exist?
Like where in the world?
Mm, this one,
Yeah, neutrino.
okay, because neutrino can be in the universe, and the neutrino has the abundant leptons. Because the neutrino has the negligible mass, so we can see in the any apparatus, okay, and we it's just the assumption. It's just assumption. We suppose we assume the unknown particle. Okay, the unknown particle that we almost can use the any operator to see it, and we regard the particle has the little mass, negligible mass. Okay,
Okay. Okay.
understand now?
Yeah.
Okay, and look at this one. This one. Okay. This one, that we use the energy of a photon. Okay, this photon is the equation. Okay, this the h is the constant. The constant is the Planck constant. Okay, and the f is the frequency. Okay, and the product of the Planck constant and frequency represent the energy of the photon. Understand?
Yeah.
Okay, and we also can regard the photon as the same as the electron. Okay, so photon maybe is the electron and the electron is the photon. Okay, understand? No problem.
Okay.
Okay, look at this one. Okay, here is the symmetry of the standard model. Okay, we will use the quarks to compose the proton and neutron. Okay, and look at this one. Okay, this is the matter, the base matter quarks. Okay, here's the anti-quarks. Okay, and you can see there's the only difference is about this one, the charge, right? Okay, the charge has changed, and the other property unchanged, right? Understand? No problem now. Okay, and look at this one. Okay, and this one we are going to learn the antimatter. Okay, first the antimatter. Okay, the universe we know is made up of the matter particle. Okay, the matter particle like the proton, the neutron, or electron, and so on, and all the matter particles has corresponding antimatter counterpart. Okay, the antimatter particle are identical to their matter counterpart, but with the opposite charge, right? So there's the one thing that is the differ. The difference is the opposite charge, right? The other property unchanged, right? No problem. Okay.
Yeah. Okay.
Okay, and this means if the one particle is the positive and the antimatter must be the negative, okay, and the same charge quantity. Okay, the first one. The matter electron, okay, the charge is the negative one, okay, and we call the new name of about the antimatter of electron is the position, okay. So if we see the position in the topic, okay, and we will know the position is the antimatter of the electron, right? Understand now?
Yeah.
Has the positive charge, okay. And how about the proton? The proton, the charge is the positive one, and the corresponding antimatter, this is this one has the negative charge, right? The neutron is zero, so the charge unchanged. Okay, but here's this one is bar. Okay, and how about the neutrino? The neutrino is the zero, and the anti-neutrino, here's the bar in the top of the sign, right? And the charge is zero. Okay, understand now? Okay, and this one. Okay, this one, the mass of the matter and antimatter. Although antimatter particle has to have the opposite charge to their matter counterpart, they still have the identical mass and the rest mass energy. Okay, the rest mass energy of the particle is the energy equivalent to the mass of the particle at rest. Okay, understand?
Yeah.
No problem.
Yeah. Okay.
Okay, and this one. Okay, look at that. Here's the mass. Has the mass in the proton, neutron, and the electron. Okay, you can see the proton, the mass is the 1.67 and times the 10 negative 27. Okay, the rest mass energy is the ME voltage, right? Okay, and you can see here's the electron, the position. Okay, the mass is the 9.11 times the 10 negative 31. Okay, and the neutrino has no energy, right? No mass energy because it has no mass, okay? No mass represent the no energy, right? No rest mass energy, okay? No problem, 是不是啊 right?
Yeah.
Okay. And look at this one. Okay. This one that we will use the conservation laws in the particle physics, okay? And the conservation laws in the particle, okay? That we use this one. The first one is the charge conservation. Okay, so if we want to know the equation is correct or not, then we'll think the conservation charge is the positive one and negative one and 2/3. Okay, no problem.
Yeah. Okay.
Okay, so if we want to know is the equation, okay, is the conservation of a charge or not, then we use the left side charge, okay, the charge total in the left side of the equation left side, okay, equal the right side of the equation, right? Understand? Okay. And besides, another conservation in the charge in the particle, microscopic particle. And in this chapter, we are going to learn a new conservation of the bio number. Okay. The bio number, okay. If the particle is the bion, okay, this one that we will use the one to represent. Okay, if you are not, this is zero. Okay, understand? No problem. Mm-hmm. So if we want to verify the equation is conservation of the bio number or not, if we found this the particle is the bion, right? Okay, and we will use the positive one. Okay, then we use the positive one to represent the charge, represent the particle. Okay, if this particle is not bion, okay, it's not type of the bion. Okay, and then we'll use the zero to represent, right? Understand that? Mm-hmm. No
Okay.
problem.
Yeah.
Okay, so if you are the anti-bion, right? So if you are the anti-proton, okay, the anti-proton is the one type of the anti-bion, right? The anti-bion, the bio number that we call the negative one. Okay, understand that because you are the anti, right? So if you are the proton, okay, then we'll call the bio number is positive one. But you are the anti, right? Antimatter. Okay, the antimatter, the bio number is the negative one. Okay, no problem.
No problem.
Okay, and besides that, the third conservation in the particle is the conservation of the lepton. Okay, another one is similar to the bio number. The lepton number is the number of lepton in the interaction. Okay, and L depends on whether the particle is the lepton or not, or you are the anti-lepton. Okay, so same as the bio number. So if you are lepton particle, okay, so you have the lepton number is the positive one. And if you are the anti-lepton, okay, so you have the lepton number is the negative one, okay. And if you are not particle of lepton, okay, so they will use the dorsal to represent. Okay, understand it?
Okay.
Like this one. Okay, no problem. Okay, and look at this one. And this work example, and we want to show that the bio number is conserved or not in the beta decay. Okay, so the beta is the electron, right? Okay, minus beta. Okay, and look at the equation. Okay, think about how to verify the conservation of a bio or not.
Neutron and proton is baryon, and the
Think about
rest
this
is
way.
not.
Hello?
Yeah, I said that neutron and proton is baryon, and then the rest is not.
Okay, first that we use this one to represent. Okay, the positive one the positive one, right? This one represents because the neutral number is the bion, right? No problem.
Yeah.
And the proton is the positive one, okay? And this one is the electron, right? Electron is one type of lepton, not the bion. So that we call this one is the zero, right? And how about the anti? The anti-neutrino of the electron, okay, is also the zero, right? Because they are not bion, right? They are lepton. No problem. And we found the left side equal the right side, okay? So the equation is conserved of the bio number. No problem.
No problem.
Okay. Okay. Look at this for example. If the left number is conserved in the following decay, and want us to identify whether the particle X should be a neutrino or anti-neutrino. Okay. To think about this one as X is the neutrino or anti-neutrino. Mm-hmm. Use the conservation of the left number. Use the conservation of the left number.
Uh, it should be neutrino
Why neutrino? Why not anti-neutrino?
because both sides have to be the same.
Yeah. And the left side is the left number is what? Total left
Uh,
number is what?
1.
The neutron is the other, right?
Yeah.
This one is the negative or positive.
Positive.
Mm-hmm. Negative.
Oh, oh.
Because this is the positive, right? The positive of the anti-muon, right? Not this one. Okay, this one that we call the left number is the positive one, okay?
Okay.
This is the antimatter of the muon, right? Okay. And the proton is what? It's the other, right? So the x, if we want the equation is conservation of left number, okay? So the x must be the left number is the negative one, right?
Yeah.
Okay. And the neutrino, okay, the neutrino muon is the anti or neutrino or non anti-neutrino. Mm-hmm. Now the x is the anti-neutrino or non anti-neutrino.
Be anti.
Okay, and then we used this one, use this one, the equation to verify the equation is conservation of the lepton or not. Understand? This is the process. The every time when you meet the topic want you to verify a lepton number is conserved or not, then you must use this one, right? The equation, right? Use the equation to verify. Okay, understand?
Okay.
Okay, no problem. Okay, and here's the conclusion. Okay, and here's the explanation, right? If the explanation in this topic, if the lepton number must be conserved, the x must also has the lepton number is the -1. Okay, so the top must have the 3 marks. The first 1 mark goes for this equation. Okay, the second mark goes to the explanation, and the third mark goes to the explanation. Okay, understand?
Okay. Yeah.
Yeah. Okay, and for the particle interaction equation, okay, all the particle interaction must obey a set of conservation law. Okay, and the conservation here first is the charge quantity. Okay, if we want to verify the equation is conservative. Okay, there are 5 laws to verify is the conservation or not. First is the charge quantity, right? The charge conservation. The second is the bio number. Okay, bio number conservation. And the third is lepton number conservation. And the fourth one is the energy conservation, right? And the final one is momentum. Okay, and quant in this chapter we learn the quant number, such as the charge quantity, the bio number and lepton number can only take discrete value. Okay, understand? And look at the work example. Okay, work example. The reaction that is proposed to create antiproton in a laboratory is shown below. And one asks the top as given the equation, okay? And one asks to determine whether the reaction is permitted. Okay, how to solve the equation? Mm-hmm. Which laws that we use?
I think
Mm-hmm.
baryon.
And
Charge.
mm-hmm. Is there anything else?
Uh,
Do we need the lepton? Do we
forgot.
need that?
I forgot if pion is lepton.
Okay, the pion is the method, right? Pion is lap. Pion is the method, not pion is the method, not lepton.
Oh,
Okay.
okay.
Okay, so the problem that we use the conservation of the church. Okay, so first let us determine the conservation of the church. Okay, and we know the proton, the charge is the positive one, right? And another proton is 41, right? Okay, and the right side of the equation, this one is 41 and one, the goal one, and the final this one because pion is the right. Okay, this one is the -1. Okay, understand? So
Okay.
we found the conservation about the charge is conservation. Okay, no problem. And step two, let to determine the conservation of the bio number. Okay, let's determine the conservation of bio number. Biome B. Okay, there are 2 biome on the left side, and each with the biome number. The B is +1. Okay, the proton and the biome. On the right hand side, we can see the 2 proton each with the biome number is the +1. Okay, one pion, the pion with the biome number. Why is the not biome number? Because the pion is meson, right? The
Yeah.
meson not the biome, right? So we call this one is call this one is 1. Okay, and another is the antiproton. The antimatter has the bio number is the -1. Okay, and we found that the conservation is conservation or not. Mm-hmm. a left hand side equal to right hand side or
No.
not? No. So we can got the conclusion. The conservation, the not conserved, right? Not conserved of bio number. Okay. So the reaction may not permitted, right? Understand?
Yeah.
Okay. This is the conclusion, right? Conclusion. Okay. Here is the process. Here's the process. It's one. First, every time the topic we we first to calculate the conservation of the charge. Remember, okay, the charge conservation is always the first one, the first step. Okay, second, we calculate the conservation of a bio number or lambda number. Okay, understand? No problem.
Yeah.
Okay, and look at this one. Let's for example. Okay, the equation is about the beta minus decay. Okay, and using the quark model of the beta decay, prove that the charge is conserved in the equation. Mm-hmm. How to verify? Using the quark model of beta decay to prove that the charge is conserved in the equation.
Plus 2 over 3 minus 1 over 3 minus 1 over 3.
Okay, so the neutron, right?
Yeah.
And this one, use this one. Okay, no problem.
And then 1 turns into minus 1 over 3 becomes plus 2 over 3
Mm-hmm.
to lose the electron charge.
Okay, understand now?
Yeah.
Okay, this one. After we have another particle, the basic unit, the basic composition of the particle, okay, and we are going to explore the structure of the matter, okay, and we want to know why the atom, okay, the structure of relay about the atom is the electron, why is the in the core is the combination of the neutron and the proton, okay, and here's the equipment, okay, the equipment is the alpha particle scattering, okay, it is the alpha particle scattering that proves the structure of the atom, okay? And the scientist is Rutherford, okay? The evidence for structure of the atom is discovered by the Rutherford, okay? And the Rutherford used the alpha source, the laser, and to collide with the gold foil, right? The gold foil. And there's the three three phenomena. The first is this one. Okay, we found that the most of the alpha particle that go straightly, right, to pass
Yeah.
through the atom, okay, and a little has a little deflection, okay. The deflection angle is less than a 10 degree, okay, and almost a few little, that is the reflection, right? Understand? Rebounding, okay, understand?
Okay.
And here is the conclusion and the result. Okay, so when alpha particle are fired at thin gold foil, most of them go straight through, but a small number burns the street. Okay, number. And we found that the result from this experiment, the first is the phenomena. The majority, remember this word, majority. Okay, the majority of alpha particle, one straight, right, gold straight, right? The wind straight through the gold foil without any deflection, right? Understand? And this represent the conclusion is it is suggested the atom is mainly empty space, right? Understand? Here is the result. Here is the conclusion, right? Mm-hmm. Understand?
Yeah. Yeah.
Okay, no problem.
Well,
And the second result is some alpha particle deflected through the small angle. The small angle, the small angle is less than the 10 degree, right? And it is the result that suggested there is the positive nucleus. Okay, there is a positive nucleus at the center because we know there's the rebelling force, right? Okay, the positive to the positive, there's the repulsive force. Okay, no, no problem.
yeah.
Understand? Okay, it's one. The third result is only a small number of alpha particles deflected straight back at angle, and the angle is the greater than the 90 degree, okay, which is the reflection, right? Okay, and this suggested that nucleus is extremely small, first extremely small, and this is where the mass and the charge of the atom is concentrated, okay? Or you can see it is therefore calculated the atom consists of a small, dense, positive charge nuclei. Okay, understand? Okay, so we have to memorize all of the results and the corresponding the conclusion, right? Okay, like if like the first is the majority of our particle when straight through the gold foil represent the atom is many empty space. Okay, understand?
Yeah.
Okay, so if we found the some alpha particle deflected through the small angle, like 10 angle, and this suggested there's the one positive nucleus on the cylinder. Okay, because we know there's the repulsive, right? Okay, repulsive force. And the final, if we found that there's the small number of alpha particle deflected back like the reflection, right? The angle is the greater than the 90 degree. And this phenomena suggests that nucleus is extremely small and there's the small dense positively charged, right? Understand now?
Yeah. Yeah. Understand.
Okay. Lucas one. So we can construct the real structure, the real model about the atom. Okay, so we can see the core. The core is the combination of the neutron, right? Neutron and proton. So we call this one as nucleon, right? This is one is the nucleon. Okay, the nucleon is the combination of the proton and the neutron. Okay, and this one is the discreting. This one is negative electron, right? Understand? Okay.
Yeah.
Okay. And look at this work example. Okay. The work example is the alpha particle scattering experiment. A student set up the apparatus below, determine the number n of a alpha particle incident per unit time on a detector held on a various angle theta. Okay, look at the equipment. In following the graph, the topic want us to choose which graph is the best representative of the variation of the n with the theta from 0 to 90 degree. Okay, choose which one. And think about this x-axis. The x-axis represent the angle, okay, the deflection angle, okay? And the y-axis is the number, okay, the alpha particle number.
I think
Y is A,
because most of them is deflected at 10 degrees.
yes, because we know the majority, right? A few of, and a little, right? Okay,
Yeah.
because the majority of go straightly, right, through the cylinder. Okay, no problem. So we choose the final answer is A. Okay. And also, in the previous, okay, here's the model. Okay, here's the model, the changing model of atomic structure. Okay, in the past, we think the atomic structure is like the pudding. Okay, like a pudding. The pudding is the combination like the electron and the proton and the neutron, right? And they combine together. Okay, not separating, right? No any separating. Okay, and this is the John and the Thomson's assumption. Okay, and we call this model is the Pudding's model. Okay, in the past, right? And according to the Rutherford's equipment of the Goldfall experiment, we found that the the reality is not the pudding, right? The model, the structure of the atom is not pudding, right? It is the atomic of the structure of the atom. Okay, we found that the core. The core is the combination of the protein and the neutron, not the three combination, right? Okay, and the outer part is the electron number. Okay, understand it? So we have to memorize this one. The pudding model is goes to the Thomson's model, right? Because Thomson think the electron and the proton and the neutron, right? Is the total combination. It's a three-part combination, right? Understand?
Okay.
And by Rutherford is the one the assumption, the introduce the now, right, is the real structure of the atomic. Okay, understand? No problem. And the equipment we call the golden Ford experiment. Okay, like the alpha scattering equipment. Okay, no problem.
Okay.
Okay, and this one. Okay, here's the history. Okay, and look at this one. Okay, this one is the new phenomena. The phenomena is the thermomonic emission. Okay, and like if we heat it, okay, if we increase the temperature of the metal, okay, when the metals are heated, and we know the conduction electrons within will gain the energy, right? The
Yeah.
energy kinetic energy. Okay, so if they electrons gain sufficient kinetic energy, okay, so they have the ability to leave the surface of the metal, right? Okay, and this phenomenon, okay, this phenomenon that we call this emission, right? Okay,
Okay.
understand, right? Okay, it's similar to the photoelectric effect. Okay, so if we found if there is the any heating on the metal, okay, and the electrons, okay, and leaves from the surface of metal, okay, and this phenomenon that we call thermomic emission, right? Understand?
Yeah.
Okay, and this is the emission, okay, and first one. Once the electron gain sufficient kinetic energy, okay, and they are released from the metal surface, okay, and when they leave the surface of the metal, okay, this one, okay, and there goes into the region. The region is the endo, right? Okay, in this dipole, right? Okay, it's endo. In this endo, okay, it's like there will be accelerated, okay, there will be accelerated in the electric field, okay, or or the deflection in the magnetic field. Understand?
Okay.
Okay. So after the electron, okay, the gain kinetic energy, the electron has left the surface of the metal, okay, and they will go into the new region. The region may be the electron neutron or electron region or the magnetic field, okay? And in this new field, there will happen a accelerated in the electric field or the deflection in the magnetic field, okay? Understand now? No
Okay.
problem.
Yeah.
Okay. And look at the work example, okay? Here's the work example. The electrons gone use electric field to accelerate electrons to very high speed, okay, to accelerate the electrons, okay, like the electron will gain high energy, right? High kinetic energy. Show that the topic one asks to show that an electron accelerated from rest across the potential difference of the 5K voltage attains the speed is the 4.2 and times the 10.7 meter per second. So use the following data. Okay, how to calculate? Think about it and tell me the process.
Think calculate the energy first.
What?
Calculate energy.
Yeah.
Uh,
And we want to show the energy,
okay,
the kinetic.
kinetic energy.
Yeah. And we separate the variable into the speed. The final result is the speed. Okay.
Yeah,
After you have calculated the kinetic energy, okay, and the final result that will be expressed in the speed. Okay. A topic want us to show that, okay, the final speed of the electron is the 4.2 and times the 10.7. Okay. So we will use the energy transfer. Okay. The electron goes into the electric field, okay? They will gain the energy, right? The energy is the electrical energy transfer into the kinetic energy, okay? So in that, the electric energy, the formula is what? Mm-hmm. It's the QV, right?
yeah, QV.
Okay, the QV, okay. And this one is the energy of the kinetic energy. The kinetic equal, okay, the electrical energy transfer into the kinetic energy, okay? This one, no problem.
Yeah,
Okay, and so we take the variable into the equation. Okay, the q is what? The q is what? The q is what? The q is the charge, right?
yeah, 1.6 times 10 to negative 19.
Okay, no problem. And how about the v? The v is what? The v is what?
5,000.
Yeah, no problem. Okay, and take the quantity, the known quantity into equation. Okay, and the mass is what?
Then 9.11 times 10 to negative
Okay, no
31.
problem. Okay, and we're separating. Okay, separating the v square. Okay, the left hand side. Okay, so the double QV, right? And over m, no problem. This is the result is the v square. Okay, and
Yeah,
finally we want to got the speed of the electrons, the final speed. Okay, and the square root. This one. Okay, no problem.
okay.
Okay, so if you take the known quantity into the equation, okay, the formula, okay, and we calculate the final answer is approximately about the 4.2 times 10 and 7, okay, so we got the right answer, okay. This is to show that process, okay,
Okay.
shooting process, okay, no problem. Look at it. The first that we use this one, okay, if we write in this one, okay, so we will got 1 mark, okay, and after that, and we separating the variable, okay, the process, okay, and we'll get another, and the final we got the right answer, okay, got another mark, okay, the total mark is 3. The problem,
No problem.
okay, look at this one, okay, this one is the new equipment. The new equipment is the particle accelerator, okay, the accelerator is like the energy gaining, right? Tra- Transfer the electric energy into the kinetic energy of electrons or charged particle. Okay, and another one is a detector. Okay, the first equipment is the linear accelerator. Okay, a linear accelerator is the type of the particle accelerator, and that will accelerate ions. Okay, or accelerate the charged particle. Okay, into the very high speed, like gain the kinetic energy. Okay, in a straight line. No problem. Okay, and this linear accelerator use the electric field within and between the metallic, right? The metallic tubes, which act as the a positively charged electrode. Okay, the high energy ions produced or use the collider experiment. Okay, this experiment enabled the internal structure of the atoms and subatomic particle to be investigated. Okay, look at this one. Okay, here is the alternating current power supply, and here is the charged particle. Okay, the ions, right? Maybe the charged particle, and this is the node, right? Okay, electron node, right? And in this gap, okay, the charge particle will be accelerated in the process. Okay, no problem.
Okay, no
Mm-hmm.
problem.
Okay, so the line, okay, so the line accelerator is comprised of the series of the hollow cylindrical tubes. Okay, look at the detailed process. This one. Okay, here's the alternating power supply is collected across each tube to ensure ions are always accelerated from one to the next one. Okay, and the ions will be attracted to the midpoint of the tube. Okay, at this point, the alternating supply will switch such that the ions are repelled to exit and attracted to the next tube. Okay, and this process continues in a straight line all the way to the end of the accelerator. No problem. Okay, understand.
Yeah, okay.
Okay, and okay, another process is the frequency, and the frequency is controlled by the AC supply. Okay, so the frequency in the AC supply is to keep the constant. Okay, it's fixed. Okay, the which means the polarity, the positive or negative, okay, of the each tube, and switch at the constant rate. May the positive the will switch into the negative, okay, and the negative will switch into the positive, okay, and therefore, and you can see the tube must be built successively longer. Okay, this is a condition. Okay, remember, the each tube must be built successively longer. Okay, the reason is the ions must be speeding up. Okay, so we want to ensure the ions spend the same amount of time. Okay, spend the same time under the accelerating. Okay, the accelerating in the each tube. Okay, understand?
Okay.
Okay, and this charge particle accelerator about the line accelerator is very important because the past paper, okay, the every year have the some several of the topic to want us to write down the process of the AC power supply and the detailed procedure, okay, and the condition. Understand? So we have to memorize all the detail. Understand? Okay, understand?
Yeah, understand.
Okay, look at another. After we have another detailed process about the particle accelerator is the linear accelerator. Okay, and here's another accelerator that is a cyclotron. Okay, the cyclotron is the another type of a particle accelerator. Okay, and pathway is not different from the linear. Okay, it's the spiral path. It's the spiral path. Okay, and the spiral path like this one. Okay, like this one. This one. Okay, this pathway. Okay, okay, and the final we can get in this gap, the out, we can get the high speed proton beam, right? No problem. Okay. Mm-hmm. And here's the uniform field in the disk, right? Here's the uniform. Okay. And here's the source of the proton. Okay, here's the source. The first cyclotron is the type of the particle accelerator, and they will accelerate ions from a central entry point around the spiral path. Okay, and they are used for medical research. Okay, used for the medical research, like the tracer. Okay, the medical isotype tracer. Okay, or the creating high energy beam of the radiation. Okay, understand? Or radiotherapy. Okay, and remember this one. This is the important. I will highlight this one. Okay, this is a detailed process. Okay, in a cyclotron accelerator are comprised of the three part. The first part is the two hollow semicircular electrode. Okay, and we call this is D's. Okay, and I introduced the D's. Okay, understand? It's D's. Another part is the uniform magnetic field. Okay, here's one. The uniform magnetic field. Okay, applied perpendicular to the electrode. Okay, electrodes. And the third part is the AC, the alternating power supply. The alternating power supply applied across the HD, and which create an electric field in the gap between them. Okay, because there's the electric field, so the charged particle will be accelerated in this gap, right? Okay, because there's the energy transferring, the electrical energy transfer into the kinetic energy. Okay, and in this part, the charged particle will deflected in the region, will be deflected in the region. Okay, understand?
How is the electric field created?
Okay, because we have in the bottom we have have source. The source, the another equipment that will provide the electric field or the magnetic field. Understand? Mm-hmm. I mean, in the bottom, okay, in the bottom, in the bottom of the section train, okay, and we have the another apparatus, the apparatus like the magnets, okay, and that will produce a upward magnetic uniform magnetic field, right? Okay, and in the middle, here's the alternating. Okay, here's the alternating supply. Okay, the alternating supply that will provide the electric field. Okay, understand? Mm-hmm.
Yeah,
Now you understand?
I understand.
Okay, so this is just a simple graph to describe how is the charge particle is accelerated or how the charge particle is deflected in the magnetic field. Okay. Oh, okay. So as for the production of the magnetic field and the charge particle, okay, the electric field is produced by another apparatus. Okay, understand? Okay. So you have to memorize the three key point. The first is there's the two hollow. Okay, here's the two hollow. Okay, here's the two hollow semicircular electrodes like D, called Ds. And the second is the uniform. Here's the uniform magnetic field. Okay, and applied. is a downward. The downward is perpendicular to the electrodes. Okay, and the third one is the alternating current power supply is applied across the HD. Okay, and this will create electric field in a gap between them. Okay, so the charged particle is only accelerated, is only inserted in this region. Okay, the charged particle is only accelerated in this region. Okay, and not be accelerated in this part and this part. Okay, so in this part there only deflection. Okay, understand now?
Okay, yeah.
Okay, and look at that. This one. Okay, here's the detailed process of accelerating ion in a cyclotron. Okay, so here's the 6 point that we have to memorize. The first is the source of charged particle is placed at a center. Okay, and second, the magnetic field in the electrode makes the follow a circular path. Okay, because they are doing a circular motion, right? Have the radius. Okay, and the second is the potential difference. Okay, the potential difference applied between the electrode accelerates the ions across the gap to next D, right? There, because there is the electric field. Okay, and we know the electric energy will transfer into the kinetic energy of the charged particle. Okay, and the fourth one is the in the next D, the ions will continue moving in a circular path. Okay, because there is the magnetic field. Okay, and the final, and this process will be repeated as the particle spiral outward and eventually have the speed of large, large enough to exit the cyclotron. Okay, understand now?
Okay.
Okay, and this alternating potential difference is needed. Okay, this is necessary. We must have the alternating potential difference because we need this one to accelerate the particle across the gap between the opposite electrodes. Okay, otherwise the ions will only speed in one direction. Okay, and as for there's the particle detector. Okay, here's the particle detector. Okay, in this process the particle detector. Okay, when a charged particle moves through any medium, like the gas or anything else, and they transfer energy to it. Okay, and this is unit through the process is ionization, right? Ionization, 对不对? Understand?
Okay.
Okay. As for this energy, there is the high energy ions transfer some of their energy to surrounding atom, okay? And removing the electrons. And the ions and the electrons produced are then accelerated by the applied electric field. Okay, so once they are discharged, they form pulses of electric current, and each pulse of the electricity is counted by the electronic counters collected by the electrodes. Okay, and the final, remember this one. Ionization is the principle by which may the particle detectors operate. Okay, and remember this one. The particles are sometimes deflected, means they are scattered. Okay, understand? Okay,
Yeah, okay.
okay. And the final, look at the line accelerator only use the electric field. Okay, only use the electric field to accelerate ions in a straight line. Okay, here's the difference between to compare with the secondary and the linear accelerator. Okay, here's the linear, the difference. The linear is only use electric field. Okay, only use electric field. There's no magnetic field, right? Because the cyclotron has the magnetic field. Okay, the linear accelerator only use electric field to accelerate ions in the straight line. Okay, but cyclotron use the electron field and also has the magnetic field. Okay, understand it?
Yeah.
No problem. And in the particle detectors, okay, then we use the two words to describe them. The first is ionization, okay, ionization, and the second is diffraction, okay, but applied by the electric field, okay, understand now?
Understand.
Okay, and look at this one. Okay, this one is for the charged particle and do the circular motion, okay, in the magnetic field. Okay, the first we want to calculate the radius. Okay, if there is the charged particle and do circular motion in the magnetic field, okay, the is the radius has the formula. Okay, then we use the laws of the magnetic force. Okay, represent the provided the centripetal force. Okay, look this way. Okay, here is the centripetal force. Okay, and you still remember the formula of the magnetic force for the charged particle is what? Mm-hmm. Is what? Mm-hmm. The magnetic force for the charged particle is what? The magnetic
Q
force
Q
is
over 4.
this one.
Oh.
Is the field density times the charge quantity and the velocity, right?
Okay,
Okay,
yeah.
and we combine this. Okay, so we know in this magnetic environmental, okay, the the charged particle that we will do the circular motion. Okay, that they will do the circular motion. Okay, so we want to calculate the radius of the charged particle in the magnetic field. Okay, and we use the magnetic force is the BQV, okay, and provide the centripetal force. The centripetal force that we use the mv squared over the radius, okay, and combine with this formula, okay, and we want to separate the radius into the left hand side, right? Okay, so the final we got the radius is what? Mm-hmm. It's BQ, right? Over MV, no problem. No, is it right?
Yeah.
Okay, and remember this one, no problem.
Oh,
First, first one, because they are doing a circular motion. Okay, a circular motion, the magnetic force provide the centripetal force. So mv squared over the radius equal to bqv. Okay, and I will separate the radius into the left hand side. And the final, the right side is the MV, the product MV over BQ, right? Okay. And this one, the MV, right? MV is the momentum, right? No problem. Because momentum is the product of the mass and velocity, right? Understand that?
yeah.
Okay. So this final, we can use the momentum over the product of the density, okay, times the charge quantity, right, to represent the radius, okay. If the charged particle do the circular motion in the magnetic field, okay, so we can use this formula to calculate. No problem now. Okay, so the radius, this one, we can use the charge quantity, right? This one, the momentum over the BQ, right? Or you can also use the mv, the mass and the velocity over BQ. No problem. Understand?
Well, yeah.
Okay. Here is the work example. There's the electron with the charge to mass. Okay, here's the charge to mass, the ratio. Okay, then we got the ratio. The ratio is the 1.8 and times the 1011 is traveling at right angles to the uniform magnetic field of flux density is the 6.2 mile Tesla. Okay, and the speed of the electron is the 3.0 times the 10 and 6 meter per second. Okay, and the topic want us to calculate the radius of the circular path traveled by the electrons. Okay, how to calculate the radius? Okay, use the logic that we just started. Mhm,
Charge to mass ratio is
mhm.
uh
The charge to mass,
Q over m.
yeah, is the Q over M.
So you have
The
to
value
flip it.
the value is the 1.8 times the 10 and 11. Okay, next step is
I think to flip it first,
okay, and then
and then times the speed. So it has mv, and then divided by the flux density.
okay, so you use this one, right?
Yeah,
Okay, you use this formula, right?
yeah,
Okay, because the radius that we just have learned, the radius use the mv over bq. Okay, and we have already know the q over m and use flipped, right? Flipped it to calculate the reciprocal of the value, right? So finally we get the 1 over the 1.8 and 10 times the 1011. Okay, and we take the lone value into the equation, right? Then finally, so we can got the radius is the 2.7 mile meter, right? No problem now.
no problem.
Okay. Okay, no problem. And here is the in the process, we have to remember the why the object do the circular motion. There's the reason why. The reason is the magnetic force is always perpendicular to the velocity of the charged particle. Okay? Because the force is perpendicular to the velocity, right? So there's no work done, right? No energy change, right? To the circular motion. No problem. Okay?
Okay.
Understand?
Yeah,
Okay. And there's no energy transfer, no work done. So the object, the charged particle, that will always do the always do the circular motion. Okay, and the magnetic force provide the centripetal force. Okay, and this one, the final, that will interpret it in the particle trees. Okay, so we want to know the radius is the any relation between the any variable. Okay, and first we have to establish the equation, the mv over bq, and the mv is the product of the momentum, right? And we can got if the radius of the track is decreasing, right? It's decreasing like the spiral closer inward, right? Like this one. Okay, like this one, right? Go this one, right? You will find the radius is decreasing, right? Like, and the object will spiral decrease inward, right?
yeah,
No problem. And this one represent the particle's moment is decreasing. Okay, understand? So
understand.
if you have found the radius of the track is decreasing, and like the phenomenon is like the spiral closer inwards, and this represent the particle's moment is decreasing. Okay, so we can know because the radius has the proportional to the momentum. Okay, and therefore the conclusion is the velocity of the particle is decreasing. Okay, and hence we can got the kinetic energy of a particle is also decreasing, right? The problem because the velocity decreasing, right? So the kinetic energy is also decreasing, right? Why is the velocity is decreasing? Because the momentum is decreasing, right? Okay, so there's the links between them. Understand?
Okay.
Okay, and the reason is due to the ionizing other particle in the past, right? Okay, now understand
Yeah.
the reason. Okay, so we got this graph, okay, and we can got this one. Okay, no problem. And the topic always want us to use the Fleming's left-hand rule to determine the sign of the particle charge. Okay, so it's this one. This one. Okay, this is the final work example. Okay, use the image shoots the red and yellow tracks in the cloud chamber. Okay, here's the cloud chamber. Okay, here is the into the page the magnetic field. Okay, and first one want us to explain how you tell from the image from the particle or antiparticle. Okay, mm-hmm.
They have
Because
opposite.
we can know this one, right?
Yeah.
Because they are decreasing inward, right? Okay, and which is the velocity decrease, right, in the cloud chamber. Okay, due to the ionization, right? Okay, so the object will go this way, right? Okay, so according to the Fleming's law, right? Fleming's left hand rule. Okay, so we can distinguish the charge, right? So the red one is the positive or negative. Hmm? Think about it. Use Fleming's use Fleming's left hand. Hmm. If you take this point, right? Take this the tangent point, right? And we can know the tropical the motion direction is the river, right? Okay, it's the river, right? Okay, and the magnetic is the interpret, right? So we have known the velocity direction, okay? We have known the magnetic field direction interpret, right? So now we use what? Use Fleming left hand rule to distinguish the charge for the red one is the positive or negative. Think
Negative.
about it.
Negative.
Why is it negative?
Because when you use the Fleming left-hand rule, it it points the force points upwards, but it's going
Okay.
downwards.
Yeah, because it's inverse, right? Okay. The opposite direction, right? So this is the negative, right? So also this one is the positive, right? No problem.
Yeah.
Okay. So that we use the cloud chamber and the pathway, right? Because in the cloud chamber the energy will decrease, right? So the pathway is inward. Okay. According to the inward direction, okay. So we choose the end point in the pathway, right? I choose this one, the point, okay. So we got direction is rightward, okay. And used we have known the direction of the magnetic field, okay. So use the Fleming's left hand to distinguish the direction is the upward, but the red one is downward, okay. So we know the particle is negative, okay. No problem now. Okay, understand. Okay, so today's lesson is over, and I will send the notes to you. Okay, and I will give a little homework. Okay, not too
Okay.
much.
Okay.
Okay, okay. Bye bye.
All right. Thank you. Bye bye.
Bye bye.
Hello, Chrisaroni.
A lot of things
Oh,
happen.
Why are they multiplying?
was he multiplying? I forgot his name. Fuck. Was it like Albert or something?
Oh my god, it flashed my eyes. Oh, I forgot.
Adorably hopping away, you.
Da 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 da. You know,
Oh my god!
没有。
I made.
你那鼓得换一下。Does this mic work? Then fuck that mic. Does this mic work? Actually, does it work? 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 I believe it works. So I just had to reset it. Alright, I think we just had to wake the mic up just like that, yeah? Goodness me gracious. Whoa. Oh. Oh my god. That is weird. Ooh. 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 Testing. 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 Test. Test. Testing.